The next thing we're going to look at in section 5.5 is the identity matrix. Really, all you need to know is it's a square matrix. It consists of a diagonal of ones from the upper left-hand corner to the lower right-hand corner, and it has zeros everywhere else. So you've actually seen this before when we solved systems of linear equations. In terms of, we did what? We converted the system of linear equations into like an augmented matrix like this, for example. And after we had converted our system of linear equations into an augmented matrix, we went through our Gauss-Jordan elimination process and ended up putting the final answer in RREF, row reduced echelon form, to spit out this matrix. And note what I just wrote down there. This square matrix is the identity matrix. And these values in our column of constants would be our results. So like, again, in this case, our result would be x equaling 7 and y equaling 11. Now we're going to apply this to other areas throughout the rest of this chapter. Example D. So what we're going to do in this case is actually use the identity matrix to come up with matrix B. All right? So what do we know? Well, here's what we know. We know that if you have the product of two matrices generate this answer, then, all right, in example letter D, we are trying to find a matrix B such that the product A, B is equal to the identity matrix I. So what we're going to do is we're going to set up a matrix equation. It's going to look like this. Now, in order for the product here to be equal to this identity matrix, this will actually be called the inverse of matrix A down the road, but we'll talk about that formally in the next section. All we have to do now is think. Let's come up with just 4 letters, 4 variables that represent the 4 entries in matrix B. So this is A, this is B, and it must be equal to matrix I. All right, so based upon what we currently know, we can do what? Well, we can actually multiply these 2 matrices together because it's a 2 by 2 times a 2 by 2. All right, so let's see how we do that. Let's review that process. So it's going to be 2A and then plus 1C, and then it's going to be 2B plus 1D, and then we're finished with all the columns and row number 1, so we move to row number 2, and then column 1 and matrix B. So this is going to be negative 2A, and then plus 2C, and then finally negative 2B, and then plus 2D. And then bring this down. So this matrix, this 2 by 2 matrix must be equal to this 2 by 2 identity matrix. All right, so we talked about equality of matrices. So with that being said, we're now able to do what? We're now able to set corresponding entries equal to one another. So let's see what happens when we do that. We get 2A plus C equals 1. Then we get a negative 2A plus 2C equaling 0. And guess what? That is a system of linear equations. All right, now let's see what happens with these entries. We would have negative B, or excuse me, we have a positive 2B plus D equaling 0. Then we'd have a negative 2B plus 2 delta equaling 1, which gives us yet another system of linear equations. So all we have to do now is solve these systems. So let's just go back to how we did this a long time ago. Let's just add using columns. All right, let's not get too fancy here. So what this would yield here is what? If we added using columns, we'd have a 3C equaling 1, which means C is 1/3. And if C is 1/3, plug it in, into either one of these equations to come up with the corresponding A value. In this case, A would be 1/3. In our second system, these cancel and we get 3D equal to 1 when we add like columns. So this is going to give us D equaling 1/3. And here again, to come up with the B value, you can plug in whatever D is equal to, 1/3, and then solve for B. In this case, B would be a -1/6. All right, so all we have to do now is say that B is equal to what? Well, remember it was B is A, B, C, D. So all we got to do is replace the A, the B, the C, and the D with the values we just came up with. So matrix B would be equal to what? There's the A value. There's the B value. There's the C value. And finally, the D value. That is matrix B. Example letter E. All we have to do, based upon these directions, is write this given system of linear equations in matrix form, all right? Which is going to look like this AX equals B. So we're not going to solve anything yet. We will solve these types of equations using matrix operations in section 5.6. But not yet. All we're going to do is set this up. So here's what it would look like. Your first matrix would be matrix A, and that's going to be the matrix of coefficients. So 2, leave a little bit of a space, -3, 4. And then this one would be what? 0x plus 2y minus 3z. And the third and final row would be 1 minus 1, and then 2z. So this is your matrix of coefficients, and it's your A matrix. And then we have to multiply matrix A by matrix X. Matrix X is going to be our column of variables in which we would be solving for if we were actually going to go ahead and solve this thing. Again, right now what we're doing is set it up. So we're just setting it up. So X, and then Y, and then Z. This is representative of matrix X. Now, this should make sense to you. Remember how to multiply. 2x minus 3y plus 4z. 2x minus 3y plus 4z. All right. So all we have to do now is set this product AX equal to Bravo, B. And B is going to be the column of constants. So what these three expressions are set equal to. In other words, that's 6, 7, and then 4. And we've finished example letter E.